Lab 1, Levitating Balloons.
For this project, we were given two balloons and we were responsible for charging them and determining the amount of electrons on the charged balloon. So we know that charge is a fundamental property of matter that can be measured. And with this, we put the same charge on each balloon in a controlled fashion so that they would repel each other in equal amounts. This way, we could assume the balloons to be equal in charge, which then made it possible to calculate since we were only able to measure the total force. We measured the repulsion in grams on a scale, and then we converted those grams to newtons, to coulombs, and then to number of electrons per balloon. After 3 trials, we found there to be an average of 6.87 times 10 to the 11th electrons on each balloon after rubbing it against a sweatshirt 10 times with an equal force.
For our models, we used a system schema to show the electric force between balloon 1 and balloon 2, and all the other forces that are within the system. The first free body diagram shows that the force of gravity is equal to the normal force, and the electric force between balloon 1 and balloon 2 are equal and opposite, which follows Newton's third law. The equations that we use include the electric force equation, the force of gravity equation. We needed to know the charge of an electron, and since we knew Coulomb's law, we knew that since the balloons had like charges, they would repel each other.
Experimental design. To test the charge of the balloons, we conducted an experiment. We first blew up two balloons in equal sizes, and then we were able to charge the previously neutral balloons by rubbing them on a sweatshirt, which transferred the electrons from the sweatshirt to the balloon. By applying a similar pressure and rubbing the balloon an equal number of times on the same spot of the sweatshirt, we were able to give an equal charge to both balloons. We then placed one balloon on a beaker and zeroed it. The beaker was used to stabilize the balloon on the scale. Then we held the other equally charged balloon above it. As we brought them closer, an electric force was created between the two charges, causing them to repel. We measured the force from the bottom balloon on the scale, and then we measured the distance between the two balloons. This was measured in grams and was eventually converted into the number of electrons.
Here are our results from our 3 trials. These include the scale reading in kilograms and the distance between the two balloons. We then multiplied the reading on the scale by the gravitational constant in order to attain the force in newtons. With this force in newtons, we could then use that to calculate the amount of charge in coulombs on each balloon. And once we had the charge in coulombs on each balloon, we could use this to calculate the total number of electrons per balloon.
For the discussion, I will talk about the physics at work in this experiment. First, we have Newton's third law, which is shown in the free body diagrams, that there are equal and opposite electric forces on the balloons. Next, we have Coulomb's law, which states that since both balloons were negatively charged, they will repel each other. Our model was accurate since all 3 of our trials yielded very similar results. We did multiple trials to make sure that our model was a good representation of electric force.
While this experiment proved to be fairly accurate, there were limitations and sources of error. The first was trying to keep the charges equal on both balloons. In our equation, we used Q to be the same number, but this may not have been the case since it was hard to get the exact number of charge on each balloon. The second was trying to hold the balloon directly above each other so that they feel the maximum electric force. Thirdly, the camera angle for determining distance r was hard to keep consistent. And lastly, while holding the balloon number 2, this may have taken away some of the charge on the balloon.